All right, welcome everyone. I'm Ole André Vadla Ravnås, and I work as a security researcher at NowSecure, where we're using Frida for security testing in mobile apps. And today I'm going to talk about Frida in the context of testing. Yesterday I did a talk on Frida in a more generic sense, or actually reverse engineering sense, but it also has applications in software testing. Basically, for those who are not familiar with Frida from before, probably most of you are not, it's a dynamic instrumentation toolkit. In technical terms, that just means it's a way to observe software as it's running and manipulate it. But one of the traits of Frida is that it's scriptable, so you can actually have a short feedback loop and quickly adapt your instrumentation to observe the software or manipulate the software that you're running. And it's multi-platform, so it works on the major OSs, and that's in continuous expansion as people contribute improvements. So like QNX was an outside improvement, for example. It's built highly modular in the sense that we use JavaScript for scripting, but you don't have to use the high-level API. You can also use the different components, even from C, C++. You can use just a low-level instrumentation yourself in tests and so on. But we'll touch on that. To give you a sense of what Frida can do, we'll start with something really simple. And that is, you have an application that's running, and you want to inject some network failures. Instead of mocking that out, you could actually do it at the API level. So you can make the application believe that it's failing to connect to establish a TCP connection. So for this demo, I'm going to use, let's see here, I'm going to use NC FTP. I'm just going to do like this, say open FTP UI.no, and I was connecting, I was logged in. However, now we could use Frida, and what we're going to do is that we're going to inject some code into this process, the NCFTP process here, so that when it calls connect, that connect operation is going to fail. And we are going to, so we're going to use a Frida API here. This is JavaScript we're writing, and we're going to inject that into there. Frida takes care of the logistics of what's happening there. So we do interceptor replace to replace an implementation of a function in memory. And then to find the function, we'll use module find export by name. And then the name of the function is connect. And we're going to use the replacement will be a native callback. So we'll get callback from native code. And the return type is int. And the argument types are int, pointer, and uint. That's what I'd find by looking at the man page of Connect, basically. So here we are inside, we have replaced implementation. Connect called making it fail, for example. And here we could now return -1, meaning it fails. But to not confuse the application, we should set errno to the error that we want to make it believe happened. So we're going to define an econ refused, which is 61 on this operating system, and set that. And then we're going to load this into the other process. So we're going to use Frida. So if you do pip install Frida tools, you get some command line tools written in Python using the Python bindings of Frida. So we can do like Frida NCFTP or process ID -L to load a script. Whoops. Oh, where did I save this? Okay, so Frida NCFTP -L agent.js. Oops. Yeah, oh yeah, it exited. I exited it. Okay. So we're just gonna start it again, and now we're gonna inject that script. And now, when we do open FTP UI NO, it should hopefully fail, and it does. Could not connect, connection refused. And you can see here that connect failed, making it fail, so the logging happened here. So when we do console log in the agent we inject, it's printed there in the console. So this way, you can inject errors or make APIs fail, operating system APIs, or internal APIs of the application and so on. So you don't even have to recompile the software, and you don't need the source code in all situations either. So that's basically the really basics of Frida. You can replace functions, you can observe them getting called without actually changing their behavior, and so forth. Okay, so we're now going to build something a bit more crazy. So hopefully we'll get through this. This is the first time going through this demo, so let's hope Murphy is not gonna intervene too much. So yeah, we have an existing application that we want to add some testing APIs to. Let's pretend we are the developers of Quake. So the question is, can we make it expose some APIs for testing? So that's good.
How did you do that?
Magic. Okay. So we're gonna turn down the volume while we're okay. So what we're going to do now, we have Quake running. That's our test application. We're going to make it expose a REST API so we can interact with it.
What's the REST API?
So you can do HTTP GET towards it to to get stuff or post to modify things. Okay. And it's like a server on the internet, basically, a web server on the internet. That's just an example. It could also expose other things, but so I'm gonna use a different editor for this. So what I have set up here, we're gonna write a Frida agent, not in JavaScript this time, but in a higher level language. We're gonna use TypeScript. So I have just some build system set up here. We're using something called Frida compile to turn the TypeScript into JavaScript and bundle it up into one script.
Did you make that font size a bit bigger?
Oh yeah. Is that readable? I think the color scheme is not that great here actually, but we're not going to use that much. So we run the compiler to compile it, and this is like Node.js stuff. What's cool is that you can reuse existing modules from Node.js in your Frida agents. So you have a whole ecosystem of modules that can be used unmodified.
Yeah, but it's also the lights have changed now. It's very hard to see.
Yeah, let's try a different color scheme here.
Yeah, but we've also got brighter lights now, which is making it even harder to see.
Hopefully that's going to be readable. Okay.
Can we just turn on the front lights here?
Yeah, lights back to the way they were.
Yeah.
No, he ran.
You ran?
It wasn't yours.
Thank you.
Okay, so so we're going to use Koa, which is an off-the-shelf module from npm, which allows us to implement the REST API very easily. So we're going to instantiate the application, Go application. We're going to instantiate the router to take care of the routes, HTTP routes. And then we're going to define the routes. So we're going to define a get status, and it's going to have these two arguments on a function here, call back for whenever someone does an HTTP get on status. And we're going to reply with a body of message hello NDC. Okay, and we're going to do app use router routes, use router allowed methods, and listen 1337 on that port. We save that, and hopefully, have a continuous compilation process running here. So now there will be an underscore agent.js here. So we can do Frida, Quake spasm, which is the name of that process, Quake. And we can have it side by side here. And we can load that compile agent, and we should enable JIT to use Frida's V8 runtime, which supports the latest features that we're going to use here. So Frida has two JavaScript runtimes. One, duct tape is the default. It's an interpreter that runs even on microcontrollers, so it's really not resource hungry at all. V8, on the other hand, is really fast, but it uses a lot more memory, but it has the latest JavaScript features. I'm going to use that for this demo, so to simplify things a bit. So it's we've loaded that script into Quake. So now we can try with curl. So yeah, localhost 1337/status, and could pipe that to JQ to pretty point the JSON, and silent mode. And here we go. So it responded with a message hello NDC. Okay, and this is still running. Let's add some more code here. For example, PID, the process ID, this process, the program could be like process enumerate modules sync to list the load libraries and then pick the first one. Save that, it auto compiles here. I can just, and the REPL here will actually reload the script. So we can just retry the request here, and you see the new output. So this way we can continuously expand our agent while it's running without actually restarting the application or even doing anything, just iterating. Okay, so let's perhaps expose something useful, like perhaps the state of this application, like the health and so on. Okay, so I know this application a bit, so I know that it has a global variable called CL, which is the client state. Actually, now I'm jumping ahead a bit. So this is what it looks like in the code. There's a client state global here, and the struct looks like this. And here, the third field, there's a stats, and that's all the different stats, like health, shells, nails, rockets, so on. So we could go and read that and expose that as a REST API. Okay, so we get a pointer to the CL structure here, and it happens to be exported by this application. It might not be in all cases, but in that case you can use debug symbols or other mechanisms. And we'll define a function read stat, and you give it a stat. Okay, so we should define a type stat. That's an enum stat. Health is 0, as we saw in the code, and shells is 6. Okay, and it returns a number. So it's actually going to do client state. So that points to the start of the structure, and we're going to add 28, which is the first fields, plus the stat is the index, times 4, because each is the size of int, which is 4. Right. And then we are going to, that's a pointer, so we need to dereference it. So we're going to do memory read int. And like this. So now we have implemented read stat. And here in the body, perhaps we can just reply with health, read stat, stat health, shells, read stat, stat shells. Okay. So if we try that now, here we go. Health is 100 and shells is 25. And if we go here and fire some bullets, like 2, this should be, shells should be reduced by 2, so it's 23. So now we're able to read out the state, the application for an HTTP GET. Okay. Sorry? What equals 1?
Yeah, if you enable gold mode.
All right. Yeah, I'm not even actually sure how I get the console. I'm not sure how it's keyed bound on this client, but okay. Right. So actually, we're cheating a bit now because we're just reading this state from an arbitrary thread or from Frida's JavaScript thread, so it's not that great. Potentially, you could be reading out the health, and then on the while the other thread, the main thread, is rendering the next frame, and then it updates the next variable, so you get like a snapshot that's inconsistent. It's not that important for this, but it will be important for the next things we're going to do. So now let's just implement it so that it does read these stats on the right thread, because we'll need that for the next parts. Okay, so this will be a bit more code, but we know that this application has a function called in, or as an input, send key events, and that's called on every frame to make the integration with SDL or whatever offload any events it has queued, like keyboard input and so on. So that's a good point to actually run our own code. So we're going to hijack that function when it's called, or hook it. So we're going to use interceptor attach. And actually now it's probably a good idea to have a function import symbol, name as a string, and then returns a native pointer. And that's just going to do module find export by name, like we did earlier, and the name. So we don't have to repeat that all the time. And we should be using that here to make that a bit more elegant. Okay. Right. Yeah. So I said we're going to intercept calls to this function. So interceptor attach, import symbol, in send key events, and we're going to give it an onEnter. And onEnter is the callback called when this function is being called. It's called synchronously. So here we can do whatever we want, like read arguments, change arguments, and so on. But we're going to define a pending here that has some pending work to do. And we'll find pending work as a function that returns anything. And here, when this in send key events gets called, we'll just drain that. So while pending length greater than 0, what's the, oops, no, sorry, pending shift, we'll grab the first one, the oldest one, and we'll call it. So we'll just iterate over, or drain this array of pending work to do and call each function. Okay. And then we're going to create a function to actually schedule some work there. So you're going to queue a function, returns a promise, so it's an asynchronous operation. And return new promise, resolve reject, and then we're going to do pending push to push a closure on this pending, so that on the next frame, when this gets called, it's going to run this code here, and that's going to try calling the function, and it's going to resolve with the result, resolve the promise. And if something goes wrong there, we're going to reject the promise with that error. Forget something, you know. Okay, so far so good. And then we're going to work on our read stat here, or actually we're going to create a read stats to read all of them. It returns a promise with the stats. And now we should probably describe what stats is. Let's say that stats has a health, which is a number, and it has shells, which is a number too. Okay, and here in read stats, we're going to return perform the closure here. So this code here is run on the right thread, and yeah, we're going to do what we did earlier, read. So health, read stat, and so on. We can just copy this code here. Okay, so we have implemented read stats. That uses the scheduling thing we added here to run things on the right thread, and that returns that. Okay, so we can now go up to our REST handler here, add async, because this is now going to be an asynchronous function, and we can do await read stats. So that will complete the HTTP GET when it gets the result from read stats. Okay, let's try that. Hopefully it will still work. Yep. Okay, so let's get to the more exciting stuff. How about if we had a post endpoint for attacking, like for firing a bullet? So yeah, we have some internal functions we can use. So we'll use in attack down and in attack up, which are called to start attacking, and when you release the mouse button, typically stop attacking. So down and up. So attack down, we'll say new native functions, and now we're going to call a function in this process. We need to import the symbol or get the address of the function to call, and then it's in attack down. And return type is void, and it has no arguments. And attack up is the same, just up. Okay. And now let's add an attack function here. Attack returns a promise void. So we're not going to return anything, but it's an asynchronous operation. And then we're going to use the perform primitive we built earlier to run this code on the right thread. So we're going to run attack down, and then we're going to attack up afterwards. But we should also keep holding the button pressed a little bit. So between these two, we're going to do a sleep for 50 milliseconds. The code completion is not helping me right now. Okay, there. Now it imported something for me. So we need to implement sleep. So that's a duration, that's a number, returns a promise void, promise resolve. And we're just going to use set timeout. Just like in a browser, you have set timeout available to schedule work. So we're going to resolve the promise after the duration has passed. Okay. So okay, now what did I? Yeah. So we have obviously need to make the attack function async to be able to await. So await perform to attack to press the button, then we wait for 50 milliseconds, and then we release the button. Okay. And now we need to expose this. So we're going to do a post/attack. And maybe you should rename the status one to just stats. That's kind of what it is. Same signature. And this is going to await attack and then respond with an empty body. Okay. So our REST handler for attack calls attack and sets an empty response. Attack will schedule on the right thread, on the rendering thread, to press the button. Then when it finishes, it will wait for 50 milliseconds and then schedule again and attack up to release the button. Hopefully it should still work here. Oh yeah, I rename it to stats. Thanks. Okay, so now we can try attack. And here we go. 18 shells, 17, 16. So it's working. Okay. Now, we did expose a REST API, but you might want a Python API instead, or you could also use an off-the-shelf module from NPM to have an IRC client or an FTP server or any kind of thing you want. But you can also just have a Python API. Oh, I'm out of time soon. So I'll just try to be really quick on this one.
I have 15 more minutes.
No, you have 15 minutes.
Oh, I do.
Yes.
Oh yeah, right. Yeah. It's early. Tells you a lot about my sleeping pattern. Yep. Okay, so we're going to use Frida's Python API. So instead of using the REPL that we used here to -l load the script, we're going to do it by hand using the Frida Python API, which is what happens behind the scenes when you use the REPL that we used. So we do Frida attach to this process here by name. We'll do enable JIT, so we use V8 as the JavaScript runtime, and then we're going to do with codecs open. Oh yeah, thanks. Agent.js, actually underscore agent.js. Cut some corners here. Source read, we're going to read the whole script. And then we're going to instantiate the script. So we do session create script with the source code. And then we do script load. And now we're going to jump over to the script. And we're going to throw away the whole REST API. So I'll just delete this. And instead, we're going to use rpc.exports. So now this script is going to expose an API that the other side can call. So we'll expose read stats. And that's an async function returning a promise with the stats. And just await read stats. Actually, I could have just doing an explicit async attack, promise void, and await attack. Oops. Okay, so we expose this API. Read stats and attack, and then we jump over here and we do agent equals script exports. So script exports is a magical object, so whatever you access on it will be turned into a function you can call. So we can now do agent. Yeah, we could like print stats before, agent read stats, and we can do agent attack, and we can do stats after, and that's it. Now we'll get the stats, we'll attack, and then we'll read the stats again. So now we can stop this, and Python 3 explore.py, and hopefully Oh. I forgot, I put it in the wrong place. Yeah. So it read it, it fired, and it read it again, and it decreased by 1, as you can see. So now we have a Python API to communicate with the agent we have running inside this process, which is a lot easier to test than a REST API probably. But you can do, you can integrate it the way you want, basically. Okay, so next I want to show something else very different. So how about detecting memory leaks in C++ code? You can already do that with ASAN and Valgrind, etc., but you can only do it at the whole process lifetime level. With Frida, you can actually do it on a really tiny scope. So just a few lines of code. You can have a guard where it checks from here to here, do you have any leaks? Okay, so we're going to use, so Frida has, the instrumentation engine of Frida is called GUM. And I'm going to stop this because it's a bit distracting. And the GUM is, has C++ bindings and JavaScript bindings that you just saw that we used. It also has C++ bindings. The C++ bindings don't cover a lot of the API yet. And you'll have to forgive me for not updating the API in some years, so the C++ looks antique. But that's something I want to fix very soon. I tried to fix it last night, but I was too tired, so I gave up. Right, do we have time to write this code? So we have something called a sanity checker. So I'll just create a ref pointer, because it's a reference counted thing. And the reason we're using a plain C exported function here is legacy. Basically, this library was built with a different C++ runtime, and it had to hide the differences between, so avoid mangling and avoid exposing the memory allocation stuff. So some legacy there should be fixed. But yeah, you can now begin checking for block leaks. And then when you're done, you can do check your end. Well, basically returns true if it succeeded, there's no leaks. You typically wrap this up into a helper class, and you just put that in your scope. But yeah, we should fix this API. Okay, so this doesn't actually do anything yet. Well, doesn't do any mistakes, make any mistakes yet. But we could make it do something silly, like do a malloc and not do a free. And we need to include this is stdlib, yeah. Because here we have some legacy code that's using malloc and free, and it's not cleaning up after itself. Yeah. Of course, yeah. That's, thanks. Thanks. Okay, so let's run this. So it tells us block leaks detected, 1 block of 6 bytes, and it's at this address. Okay, so to make this a bit more useful, we can now do checker enable backtraces for blocks of all sizes. And here you go. You see the block and the line number and where this was called from. And we can add a few more. And yeah, you see that there's 2 of size 6 and 1 of size 3. If this slows down your application too much, you can also do enable backtraces for blocks of size and just say 3, for example. I only want backtraces for the blocks that are size 3. So you can run it without backtraces first. You get because that's very cheap overhead-wise, and then you see that I'm leaking a block of 140 bytes every time. Okay, I can enable backtraces just for that block, so I don't change the behavior of the application or the timing of the application, timings of the application too much. So here, just run this. Now you see there's no backtrace for these 2, but there's for this one that we care about. Yeah, so we have some other things in this API. I won't have time to actually show them, but you have interceptor to intercept function calls, like you saw earlier, attach and replace and so on. So you can do that in tests. And there's also the backtracers are exposed. You can look up debug symbols. There's a sanity checker that we just used. There's also samplers, so you can sample things like malloc count, like how many times was malloc called, and then you can have your tests check that malloc was not called at all when these functions were called. So you could have, okay, this part of my code base is not supposed to call malloc ever, or I use any memory allocation, and then you can use such a guard or a counter, a sampler, and then you can peak the total count. So you can have there's also a call count sampler, which you can give it any functions, and it will count the number of calls to those functions. So that way you could also like count how many times certain internal functions in your application are called, and assert that they're not called, or that they are called, or how many times they're called. And if you're optimizing something, maybe you start out with asserting that malloc is called less than 1,000 times, and then you start out with 1,000,000 times, and you get towards your goal, and you have a passing test at the end. And you'll have a regression coverage if you start using a lot more, or calling malloc a lot more again, or so, something like that. You also have a profiler. These things are building on the interceptor that you saw earlier, so you can also build such building blocks yourself. The profiler, unlike traditional profilers, this one lets you put an inspector so that whenever a new worst case is detected, it can actually look at the argument list, and you can stow away some context. So say you have a function that's quite generic in nature, like in a media processing framework, you're pushing a buffer, so there's a push buffer function. And this happens to be slow just 1 in 1,000,000 times, but then it's really slow. So you're looking at the profiling data and you see, oh, it's really slow, but I don't know what it was called with. Like, what was the argument? Was it audio or video, or what was it? And this way you can add like an inspector callback. You can snapshots on into string a summary of the call that happened by looking at the argument list, and that way you have more context when looking at the report at the end. Okay, so let's taste of that. Yeah, so I'll just mention these other use cases because I won't have time to cover more. But other things you could do, you could use interceptor, and you could attach to certain functions that you know will be called from different threads. And you could add random sleeps, and that way you could add jitter to the thread scheduling and maybe shake out more bugs that way. Another thing is fuzzing. Obviously, you can hit your functions with internal functions with untrusted data, for example, if they're supposed to parse network data, and to test them from the inside, so you don't have to actually add a lot of code just for testing. So in some cases, you can avoid premature architecture by using Frida, since you don't have to necessarily make everything stubbable, like be able to replace different things of your code, parts of your code, just for testing. And I made a note somewhere here. Oh yeah, I forgot to show you. I still have 4 minutes. Well, I'll just use bin cat. Frida cat. Enable JIT, enable --debug, I think. So you actually have a debugger. So here, if you go in Chrome, here we're actually attached now to the Frida JavaScript agent. So you can use the Chrome inspector to debug your Frida agents just like Node.js process. It's the same inspector API. Anyway, I'm out of time, I think, but I have maybe room for one question. Okay, thank you.